Hello, everybody. Let's continue our tale of nucleosynthesis, of generating all the elements on the periodic table. We left off with stellar fusion, creating elements all the way up to iron. Now let's go ahead and fill out the rest of the periodic table, going to another process, the neutron capture process of nucleosynthesis. Okay, so just to give us the bigger perspective of what we're really doing here, because it is stunningly profound to just stop for a second and realize that we are talking about where all the elements on the periodic table are coming from. Remember that all the matter that you've ever really interacted with, everything that you would normally consider matter, is made up of these elements. So you are talking about the origins of the very atoms of everything that you interact with, and you yourself, where they come from. And somehow, through some sort of cosmic recycling of the birth, life, death, and a new generation of stars, these atoms have been created, and some small amount of them have ended up here creating our sun and our solar system. An even smaller amount of them have gone into creating you. And after you're gone, those same atoms will still be around and become a part of something else. All right. So now that we've grounded ourselves in a little bit of a bigger picture, let's see where we left off. So we've talked about Big Bang nucleosynthesis, the generation of hydrogen and helium that actually occurred in the Big Bang, or in the times of the Big Bang itself as a consequence of the Big Bang. And then we talked about stellar nucleosynthesis, where in the cores of stars, we're going to fuse up to iron. And we saw a couple of different ways to do that. Primarily took a look at the alpha process to produce alpha elements. And now we're going to finish things out where I really want to talk about how we can build elements past iron. Since we can't fuse things together, iron is our dead end of fusion. We can't take two iron nuclei. We can't even do a helium capture really onto an iron nucleus. So all of those end up costing energy. So that's the dead end of fusion. So how do we go about building elements that are heavier than iron? Well, we have to use a different process than fusion, and that process ends up being neutron capture, where you're going to have a nucleus, and it can be light or heavy, and you're just going to take a lonely singular neutron and add it to the nucleus, making a different isotope of the element that the neutron got added to. And then we have to look at whether or not that new isotope of that element is radioactively stable or unstable. If it's unstable, it will radioactively decay, and in doing so, it'll change its nuclear makeup, it'll change to a different element, thus moving us around on the periodic table. All right, so let's take a look at the two processes of neutron capture, the so-called S process and R process. And you might be thinking, man, I have to memorize more letters. Well, these letters are very intuitive. The S is for slow because that happens very slowly, and the R is for rapid because that happens very rapidly. All right, so let's start with the slow neutron capture process, which is usually just called the S process. Where is this happening? This is happening in asymptotic giant branch stars. Because in the cores of these asymptotic giant branch stars, remember we have our carbon oxygen ash core, and then a shell of helium fusion, and then a shell of hydrogen fusion around there. And in those fusion reactions, one of the things I didn't mention that's constantly being produced in these fusion reactions are neutrons. So we are producing a large number of neutrons in the cores of asymptotic giant branch stars, and those neutrons are then free to go out and interact with all the other atoms of that star. Particularly, we want to talk about where they're going to be interacting with in the envelope, in the outer parts of the expanding shells of the stars. All right, so being neutral, neutrons, they don't have to worry about any sort of electromagnetic repulsion from the nucleus. They can just go, boop, here I am. The positive charge of the nucleus doesn't push them away. So neutrons are easily captured by a nucleus. And what this does is it adds 1 to the mass number. Remember, the mass number is the number of protons plus the number of neutrons. You added 1 neutron, so you add 1 to the mass number. This process, we would say that that nucleus has captured a neutron. It has experienced a neutron capture. What we've done is we've created an isotope of that element. We had whatever the isotope of the element was before, say carbon 13 or carbon 12, and we'll go with 13 since I have a picture of carbon 14 down here. We added a neutron to it, changing it. It's still carbon, but it's with one extra neutron. So it's not carbon 13 anymore, it's carbon 14, a isotope of carbon. And is frequently, whenever you capture a neutron and become a different isotope, you're not becoming the stable one. You're going from a stable one, becoming an unstable isotope. So it's going to radioactively decay, primarily through a process called, well, one of the processes that it can go undergo radioactive decay is called beta decay, and that's one we want to pay attention to here. So we have carbon 14, and then that carbon 14 is unstable. It doesn't like having 6 protons and 8 neutrons. It wants to change its nuclear makeup to become something more stable. So what it'll do is it is going to convert one of the neutrons into a proton plus a antineutrino and an electron. The electron or the proton makes sense. You have a neutrally charged neutron. You want to change it into a proton, you better spit out a negatively charged electron. So that process is called beta decay. It's one of the most common radioactive decay pathways. So essentially what we're talking about is we are taking something like carbon 14, we are adding a neutron to it, or we're taking carbon 13, adding a neutron to it, making it carbon 14. It'll radioactively decay, change one of those neutrons to a proton, thus becoming element number 7 instead of element number 6. So it's going to become nitrogen, and it converted 1 neutron to 1 proton. So now it has 7 protons and 7 neutrons. So with this process of adding a neutron via neutron capture, then undergoing a radioactive decay, a beta decay, adds a proton, adds a proton to the nucleus. So we've moved up 1 on the periodic table. A more massive element is made. We have created a heavier element via a neutron capture nucleosynthesis. All right, so again, just so you can see what's going on, here's another example where you have a nucleus that's full of protons and neutrons. It's going to capture a neutron. So you can see this proton right here. So it's going to capture a neutron. And then this proton right here is going to radioactively it's going to undergo a beta decay. The nucleus will undergo a beta decay. This proton will become a neutron, shoot off an electron and an antineutrino, and thus move this up 1 on the periodic table. This process is incredibly slow, hence the name, the S process, the slow neutron capture process. The timescales for this to actually happen in asymptotic giant branch stars, for a neutron to be captured by an atom, on average, it could be years or decades before that nucleus can capture another neutron. So it has plenty of time to capture a neutron, radioactively decay to change itself to a different element, and it has plenty of time to do that before another neutron would come along. So basically, it's like pink, add a neutron, radioactive decay, go up 1 on the periodic table. A decade later, capture a neutron, undergo a radioactive decay, move up 1 on the periodic table for any given nucleus. So you have to remember that there are almost uncountably large number of atomic nuclei in a star. So this is happening all the time. But these are the timescales for any single nucleus to undergo subsequent neutron captures. So we're adding them 1 at a time. The beta decay will happen, and we'll move up 1 on the periodic table. Since this is such a slow process for any given nucleus, it's going to have 2 neutron captures over the course of like a decade. So we call this the slow neutron capture process. This process, while slow, you have to remember that these things are living for tens of thousands of years to hundreds of thousands of years on the asymptotic giant branch. You can slowly build up heavier and heavier and heavier elements all the way up to bismuth 209, which will then radioactive decay itself into lead. All right, so this slow process is primarily occurring. Where are these neutron captures happening? They're mostly happening in the atmosphere. So you remember these are the ones that are expanding outwards. So we're doing this neutron capture process, and all that material is being blown away slowly back into the interstellar medium, seeding the interstellar medium with a bunch of newly created S process elements. Oops. So let's go ahead and take a look to see how this actually operates here. Oops. And what I want to show with this is here we have the number of neutrons plus protons on the x-axis. And on the y-axis, we just have the number of protons, the element number. So this is moving up one in element number. This would be moving up one in atomic mass number, but staying the same element. And the way that the slow neutron capture process works is it'll capture a neutron, and then that'll decay to form a different isotope. Sometimes you can capture several neutrons before you undergo a beta decay, depending on how radioactive the isotope is, how often neutrons are being captured. So, but notice that you'll capture one and then you'll decay. Capture, capture, decay. So it's the slow crawl up the periodic table, but it can create over time heavier and heavier elements, elements heavier than iron. So if we look to the right of our iron peak, you can see that we have a lot of the S process elements, and you'll notice that you have some strange peaks in here. You have a peak here at strontium, you have a streak at barium, and you have a streak at the end point, lead, which is creating bismuth 209, which then decays to lead. So you have what we'd call the S process peaks littered throughout these. This one right here is an R process peak. So we have strontium, barium, and lead. You don't need to remember those details. This is just to point out that the S process is creating a lot of heavier elements, but just by the way the radioactive decay works, that you're going to preferentially create certain elements more than others, thus explaining the cosmic abundances that we see. There is a rhyme and a reason to all of this. Okay, now let's go to arguably the more exciting process, the rapid neutron capture process, the R process. Whenever I talk about the R process, I'm gonna have to talk about the older paradigm and then the emerging new paradigm, and then the reality that both are really happening. So depending on what resource you're reading about the R process, you're gonna run into both of these sort of paradigms. The old paradigm is this only occurred during core collapse supernovae explosions, which that makes sense. What happens during the core collapse? Well, the iron ash core gains enough mass to go over the Chandrasekhar mass limit. Neutron degeneracy pressure is overcome, and then those milliseconds, as the core collapses, we first had photodisintegration, and then we had neutronization. And that second part, neutronization, where we're forcing the electrons into the protons to form neutrons, that's generating a boatload of neutrons. So during the core collapse supernova, a huge number of neutrons are all created all at the same time that are then going to get caught up in the supernova explosion, mixing those neutrons with all the other atomic nuclei that are around. So now we're not talking about, oh, I'll capture a neutron and wait a decade to capture another neutron. It's basically just like pouring a whole pile of neutrons on atomic nuclei all at once. So you're going to dump a whole bunch of neutrons onto a single atomic nucleus, which is going to really, really jack up the mass number, but keep the element number the same, and create some pretty crazy radioactive materials. So these radioactive materials will then rapidly decay, and they'll keep undergoing radioactive decays until they can form stable, new, heavier elements. this process of capturing a whole bunch of neutrons very, very rapidly in a supernova core collapse where you're producing all those neutrons is called the rapid neutron capture process, the R process. And that is, yes, that does happen. However, as I have noted down here, over the past 5-ish years or so, we are having to mix up and we had to change that periodic table of which elements are created by which nucleosynthetic process. We've had to change it up because more and more we're understanding that with these supernovae explosions, the production of heavier elements wasn't happening fast enough to actually match our cosmic heavy element enrichments that we see occurring at different places throughout the universe. So this model, while it does happen, it was not the full story. It could not reproduce what we were observing. There had to be some other process. And that enters a new sort of a new emerging paradigm that we also have these two neutron stars in orbit around one another, which will spiral and then merge together in this fantastically powerful cosmic explosion event called a kilonova, a relatively new term in the field of astrophysics. And whenever two neutron stars are merging together, guess what there's a lot of? Available neutrons, which then, whichever atomic nuclei are around, can then pile onto our atomic nuclei, creating the R process in a different way where the energies are a little bit lower. The neutrons are moving at relatively lower energies, lower velocities whenever they interact with one another. So it can actually drive an R process in a different way. In reality, both of these are occurring and each one is creating its own suite of elements. And now let's go ahead and take a step back and take a graphical view of how this R process is working. So here, again, we have a plot on this one. The x-axis is the number of neutrons. The y-axis is the element number, so the number of protons. And here, you're just going to rapidly add a whole bunch of neutrons where you're not even on this plot anymore. And then they're going to undergo a large number of radioactive decays, decaying, until they reach what is called the island of stability. They become a stable atomic nucleus. So it's no longer like the slow one where you're just inching your way up. You're throwing on a bunch of neutrons and letting some crazy radioactive decays happen. And whatever comes out in the wash, those are the elements created by the R process. Now, interestingly, the S process and the R process are do not create a completely different set of elements. The S process does create some elements only. The R process also has its own set of unique elements that it creates, but then there are some elements that are created by both the S and the R process, and by things like fusion in the cores of stars. So, excuse me. So a lot of these processes, these nucleosynthesis processes overlap with one another. And all that can go into explaining the cosmic abundances. Okay, so that's what I have on nucleosynthesis, but I want to wrap up this discussion by integrating all the knowledge that we've gained recently about the life and death of stars and now nucleosynthesis. And I want to take a step back and look at the big cosmic picture and see that we have really, really unearthed something amazing. We've pulled back the veil on the universe, and we're seeing a grand cosmic recycling and a slow fundamental shift of the composition of the universe over time. So what is actually happening? And notice that this is a recycling. It has no beginning or end, really. So let's just pick to start by forming new stars. What are we forming new stars out of? We're forming new stars out of the interstellar medium. We have these nebulae, we have these molecular clouds that are mostly hydrogen and helium, but they have some number of metals, all of these heavier elements that we just created through stellar fusion nucleosynthesis and neutron capture nucleosynthesis. We're going to form these molecular clouds out of the interstellar medium, which will then undergo their collapse, their protostar phases, to form stars and planetary systems. Where does the solid stuff that our Earth is built out of and you and I are built out of come from? All the elements that are heavier than hydrogen and helium. So we can now build the planets because these heavier elements forged in the cores of stars and by the S&R process are in these molecular clouds. So now we form these new stars with planetary systems. They live out their life. We form stars according to the initial mass function, where we form some high mass stars, some small number of high mass stars, and a whole bunch of low mass stars. They evolve towards their death. The low mass stars and high mass stars fusing hydrogen to helium, helium into carbon and oxygen, but that would mark the death of a low mass star, which will then go through the asymptotic giant branch and end its life as a planetary nebula. And during the asymptotic giant branch star, it's going to be generating new, heavier elements by the S process. And some of those fusion processes that built up to carbon and oxygen in its core get mixed into the envelope and go out with the expanding shell as well. We have enriched the interstellar medium by the death of a low mass star with low mass stellar fusion nucleosynthesis products and S process nucleosynthesis products. The high mass stars live very, very rapidly and they explode in supernovae explosions, which can drive the R process. Also, in the cores of these stars, we had the alpha process happening, creating all of those elements up to iron and all of those nice evenly numbered elements, the alpha elements. And in the supernova explosion, boom, those get seeded back out into the interstellar medium. And also during the supernova explosion, we build all those R process elements. What gets left behind by some of the supernova explosions? Neutron stars, which you can form binary neutron stars, which then can merge and have an R process. And whenever that kilonova happens, it's going to seed the interstellar medium with all of these newly created heavier elements. Which brings us back to an interstellar medium that's now enriched. The net amount of metals has gone up to kick off another round, another generation of forming stars, going through all the nucleosynthesis processes, the stellar fusion ones and the neutron capture ones. And those are going to get injected, further enriching the interstellar medium over and over and over and over and over again. And this becomes a huge topic whenever we talk about the evolution of galaxies and the evolution of the universe itself. Because as, say, a galaxy ages, it's going through several rounds of star formation, enriching in heavier elements, injecting those back into the ISM, forming a new round of stars, making even more heavier elements, injecting those back into the ISM. So we can see over time that galaxies become more metal enriched. The older the galaxy, the higher the metallicity. We have this grand cosmic recycling where we're creating all of these new elements, and most everything that went into making the star gets re-injected but slightly altered back into the interstellar medium. I find that nice cyclical relationship an absolutely beautiful part of understanding and integrating all of this knowledge. I hope you have an appreciation for all of that. And hey, I mean, worst case scenario, you have a deeper understanding of the periodic table now and the universe. All right, thanks. That's all I have for nucleosynthesis. I will see you when we start to talk about neutron stars, black holes, and all the weirdness that comes with relativity.